the ground trembles first. Not violently. Not with the sudden shock of an explosion. It begins as a slow vibration beneath the pavement, so faint that most people do not notice it at all. But the men standing in the shadow of the building feel it immediately. For stories of brick and steel rise above them, a structure that has stood for decades. Its windows are dark. Its walls carry the stains of 100 winters. From the outside it appears solid, permanent, one more immovable piece of the city. Then the machines begin to move. Deep beneath the building, hidden from the street, massive steel cylinders extend outward with quiet mechanical patience. Each piston slides forward slowly, pressing against the foundations that have supported the structure for generations. Hydraulic pressure climbs. Hundreds of tons of force gather inside pipes no wider than a man's arm. Above ground, the building begins to shift. It is almost imperceptible at first. A faint cracking sound moves through the masonry as decades-old mortar fractures under the growing pressure. Dust drifts from window frames. A long seam appears along the side wall where brick meets brick. Still, there is no explosion. No roaring engines. Only the quiet insistence of the machines below. Another piston extends. Then another. The structure shudders once, like a giant drawing a final breath. And suddenly the entire building collapses inward. Floors fall onto floors in a cascade of shattered beams and crumbling brick. Steel girders twist and snap beneath the weight of the falling structure. A cloud of dust surges outward across the street, swallowing the block in a storm of powdered concrete and drifting debris. Where a building stood moments ago, there is now only a mountain of broken material. The machines beneath the rubble fall silent. They have done exactly what they were built to do. Across the 20th century, these silent giants, hydraulic demolition systems capable of generating thousands of tons of controlled force, transformed the way cities erased themselves. Entire neighborhoods vanished beneath their pressure. And the machines that made it possible rarely appeared above the ground at all. Cities are monuments to permanence. Stone is stacked upon stone. Steel is anchored into foundations buried deep beneath the earth. Concrete hardens into walls designed to withstand decades of wind, storms, and the constant vibration of urban life. Every beam, column, and support is calculated with the same goal in mind: endurance. Architects build for longevity. Engineers design structures meant to stand for generations. And yet, the history of every city contains an opposing force just as powerful as construction itself. Destruction. Urban landscapes are never truly finished. Streets that once held horse-drawn traffic must eventually carry automobiles. Factories that once powered industry become silent relics as economies evolve. Entire neighborhoods age, their buildings weakened by time, fire, or neglect. The structures that once symbolized progress slowly become obstacles to the next stage of growth. For centuries, removing those obstacles was a slow and brutal process. Workers dismantled buildings brick by brick. Timber beams were cut away by hand. Walls were weakened until gravity could finally pull them down. The process could take weeks, sometimes months. In crowded cities where space was limited and streets narrow, the danger was constant. A collapsing wall could crush nearby homes. Falling debris could kill workers or pedestrians. Entire blocks sometimes remained abandoned simply because tearing down the structures safely was too difficult. But as cities expanded through the 19th and 20th centuries, demolition could no longer remain slow. Urban growth accelerated. Railways arrived. Factories expanded. Skyscrapers began rising toward the sky. The land beneath these structures became more valuable with every passing decade, and the pressure to remove outdated buildings grew stronger. An industrial solution became necessary. If engineers could construct towers of steel hundreds of feet tall, they reasoned, then machines could also be built to remove those structures with equal precision. Demolition would have to evolve into its own form of engineering, a calculated process governed by physics, pressure, and controlled force. This transformation gave rise to a new class of machines. They did not roar like steam engines. They did not explode like dynamite. Instead, they operated quietly, hidden beneath foundations or positioned against structural supports. Using hydraulic pressure capable of generating thousands of tons of force, these machines could shift entire buildings from their foundations with slow, controlled movements. A structure designed to stand for a century could collapse in seconds. The paradox of the modern city emerged from this contradiction. Human ingenuity built enormous structures meant to resist gravity and time. Yet the same ingenuity also created silent machines powerful enough to erase those structures when progress demanded their removal. Cities were designed to endure. But the machines waiting beneath them were designed to make endurance temporary. By the late 19th century, the modern city had begun to outgrow itself. Industrial expansion had transformed urban landscapes with astonishing speed. Factories rose beside rail lines. Tenement housing filled every available block. Warehouses crowded along riverfronts and harbors where ships delivered the raw materials of industry. Within a single generation, populations doubled, sometimes tripled. But the cities themselves had not been designed for such growth. Streets that once served horse carts and pedestrians became choked with wagons, streetcars, and early automobiles. Wooden structures built quickly during earlier expansion now stood weathered and unstable. Entire districts were crowded with buildings erected decades earlier under far less demanding standards. Time had begun to weaken them. Brick walls cracked beneath shifting foundations. Timber beams sagged under the weight of additional floors added during periods of rapid construction. Old factories, abandoned when industries moved elsewhere, remained standing as hollow shells filled with rusting machinery and collapsing roofs. Fire departments considered many of these structures constant threats. A single spark could ignite aging wooden frameworks and spread through densely packed blocks before firefighters could contain the flames. Several catastrophic urban fires during the 19th century had already demonstrated how quickly entire districts could vanish under such conditions. Cities faced another problem as well. Space. Urban land had become increasingly valuable. Rail terminals required large tracts for expanding freight yards. New office towers demanded foundations deeper and stronger than older buildings could provide. Municipal governments sought wider streets, larger transit corridors, and new public infrastructure capable of supporting growing populations. But the land required for these improvements was already occupied. Rows of aging structures blocked the path of expansion. For city planners, the challenge was not simply designing new buildings. The challenge was clearing away what already existed. Removing a single warehouse might be manageable through traditional demolition methods. Removing an entire block of heavy masonry buildings inside a crowded city was something else entirely. Workers armed with hammers and ropes could dismantle structures slowly, but such methods exposed them to enormous danger. Walls weakened during demolition often collapsed unpredictably. Bricks and timber could fall into neighboring streets where pedestrians and traffic continued moving only yards away. The process consumed time that rapidly growing cities could no longer afford. Weeks spent dismantling a structure delayed construction of whatever would replace it. Investors and municipal authorities demanded faster solutions, methods capable of removing massive buildings quickly without causing uncontrolled damage to surrounding neighborhoods. The crisis forced engineers to confront a difficult question. How could structures weighing thousands of tons be brought down safely within the tight boundaries of a modern city? Explosives offered one answer, but their violent force carried unacceptable risks. Shockwaves could damage nearby buildings. Flying debris might travel far beyond the demolition site. What cities required was something more precise. A method capable of controlling enormous structural forces while keeping destruction contained within a narrow footprint. The answer would not come from explosives or brute labor. It would come from pressure applied slowly, deliberately, and with mechanical precision. Long before hydraulic systems reshaped the demolition industry, buildings were brought down through patience, gravity, and brute human effort. Demolition crews in the 19th century worked with tools that would have looked familiar centuries earlier. Iron hammers struck brick walls until mortar crumbled loose. Crowbars pried apart timber beams. Workers climbed through unstable structures, removing pieces slowly so that gravity could do the rest. The work was exhausting and unpredictable. Each wall removed weakened the structure in ways that were difficult to calculate. A beam cut too early could shift the entire building. Floors might collapse beneath workers still dismantling upper levels. Demolition was less an engineered process and more a careful negotiation with gravity. Crews often relied on ropes and teams of horses to pull weakened walls outward. Once the supports were cut, men gathered at a distance and shouted warnings before the ropes tightened. Slowly the structure leaned. Brick fractured along stress lines. Then the wall collapsed in a violent cascade of stone and dust. In crowded city blocks, the results could be chaotic. Falling masonry sometimes spilled into neighboring streets. Debris crashed through the roofs of adjacent buildings. Even experienced demolition crews could not always predict how a structure would break apart once its supports failed. The rise of steel frame construction during the late 19th century made demolition even more difficult. Earlier brick buildings relied heavily on gravity and masonry walls for support. Remove enough of the walls and the building eventually collapsed under its own weight. Steel structures were different. Their internal skeletons distributed loads across beams and columns in complex patterns. Removing a few walls no longer guaranteed collapse. A steel-framed building could remain standing even after large sections of its exterior had been stripped away. Demolition crews found themselves cutting through thick iron beams and riveted connections designed specifically to resist enormous loads. Progress slowed to a crawl. As cities expanded and building heights increased, the need for a more systematic approach to demolition became unavoidable. Engineers began studying the physics of structural failure with the same seriousness previously reserved for construction. If buildings could be designed to stand, they reasoned, then they could also be designed to fall. The key lay in understanding where a structure carried its weight. Every building rested on a network of load-bearing points, columns, supports, and foundation anchors that transferred mass toward the ground. Remove enough of these points, or apply sufficient force against them, and the balance holding the structure upright would disappear. Once that balance was broken, gravity would complete the process instantly. Early mechanical demolition tools emerged from this understanding. Wrecking balls suspended from cranes swung against walls with enormous momentum, shattering brick and concrete. Heavy cutting torches burned through steel beams that once seemed indestructible. Yet these tools remained violent and imprecise. What engineers increasingly sought was something quieter. A machine capable of delivering immense force without explosive shock. A system that could press against a structure slowly, shifting its weight until the building itself surrendered to gravity. That search would lead to the silent giants of industrial demolition, machines powered not by swinging steel or explosive charges, but by the controlled pressure of hydraulic force. The machines that would eventually reshape urban demolition did not begin in city streets. Their origins lay inside workshops where engineers studied a simple but powerful physical principle: a liquid under pressure can transmit force with extraordinary efficiency. Hydraulics had been understood for centuries. In the 17th century, scientists studying fluid behavior discovered that pressure applied to a confined liquid spreads evenly throughout the entire system. A small amount of force applied in one place could be multiplied dramatically if directed through a larger surface area somewhere else. The principle was simple. The results were enormous. By the late 19th century, engineers began harnessing hydraulic systems to power industrial presses, lifting equipment, and heavy machinery used in rail yards and factories. Steel cylinders filled with pressurized fluid could push pistons outward with forces far greater than any individual worker, or even teams of workers, could generate. Inside those cylinders, pressure often exceeded 2,000 pounds per square inch. At those levels, even a modest piston could exert several hundred tons of force. Demolition engineers quickly recognized what this meant. Instead of attacking a structure with swinging metal or explosives, a hydraulic system could apply pressure directly to the points where a building carried its weight. Slowly extending pistons could push against columns, foundation blocks, or load-bearing walls. The building would not explode or shatter immediately. Instead, it would begin to move. A typical hydraulic demolition system consisted of several essential components working together. At the center was the hydraulic pump, a machine that forced oil through thick steel pipes under extreme pressure. The pump drew energy from diesel engines or electric motors powerful enough to maintain constant pressure throughout the system. From the pump, the pressurized fluid traveled into reinforced hoses connected to hydraulic cylinders. Inside each cylinder sat a steel piston designed to slide forward when fluid pressure increased. As oil filled the chamber behind the piston, the pressure pushed the metal rod outward with immense strength. The longer the piston, the farther the extension could reach. Some demolition cylinders could extend several feet while carrying loads measured in thousands of tons. These pistons were positioned carefully around the structural core of a building. Engineers studied architectural drawings and structural calculations to determine which columns carried the greatest loads. By placing hydraulic jacks beneath these points, crews could begin shifting the building's internal balance. The movement was almost invisible at first. A column might rise a fraction of an inch. A foundation stone could crack under the pressure. Steel beams embedded in concrete floors would begin to bend as the load paths inside the structure changed. But buildings are systems of balance. Once enough supports weakened or shifted, gravity took control. The upper floors, sometimes carrying thousands of tons of concrete, steel, and masonry, lost the stable foundation that had supported them for decades. The structure folded inward under its own weight, collapsing into itself with remarkable precision. The power behind that collapse came not from explosions or violent impact. It came from fluid pressure quietly expanding inside steel cylinders. The silent giants of demolition had done their work long before the first brick fell. Hydraulic demolition machines possessed a strange quality rarely found in other industrial systems. They were powerful beyond imagination. And yet, they were almost silent. Steam engines roared with pressure. Wrecking balls crashed against walls with thunderous impact. Explosives shattered buildings in violent clouds of debris that could be heard across entire cities. Hydraulic systems did none of these things. When the pump began forcing oil through the pipes, the only sound was a low mechanical hum. The cylinders extended with slow, deliberate movement, pushing steel rods outward inch by inch. To an observer standing nearby, the process often seemed almost calm. But beneath that calm lay enormous stored energy. Hydraulic pressure concentrates force within sealed systems that can hold thousands of pounds per square inch. Inside reinforced hoses and steel cylinders, fluid becomes a carrier of potential destruction. When the system remains stable, that pressure performs useful work. When the system fails, the results can be catastrophic. A ruptured hydraulic line does not simply leak oil. Under extreme pressure, escaping fluid can burst outward with the velocity of a projectile. Engineers sometimes describe these failures as fluid jets capable of slicing through protective clothing or penetrating skin. Inside demolition sites where pressures climb above 3,000 pounds per square inch, such ruptures become deadly hazards. Cylinders themselves carry similar risks. Hydraulic pistons are built from hardened steel designed to resist tremendous loads, but even these components possess limits. If pressure rises beyond safe operating levels, the cylinder walls may fracture or seals may fail, releasing the compressed force that had been carefully contained inside the system. The sudden release of pressure can send metal fragments flying across the work site. More dangerous still are structural miscalculations. Hydraulic demolition relies on precise understanding of how a building carries its weight. Engineers study blueprints, calculate load paths, and position cylinders where pressure will weaken critical supports. If those calculations are wrong, if an unseen structural reinforcement carries more weight than expected, the building may react unpredictably. Instead of collapsing inward, it may twist. Instead of falling in a controlled direction, it may drop sideways toward surrounding streets. In dense urban environments, even a small deviation from the planned collapse path can threaten nearby structures and workers alike. Because hydraulic systems operate slowly, the warning signs of danger sometimes appear too late. A column may bend slightly more than expected. A floor may crack along an unexpected line. Within seconds, thousands of tons of material can shift in response to forces that were meant to remain controlled. The silent nature of the machines makes this danger more unsettling. There is rarely a dramatic build-up of sound before the moment of failure. No roar of engines announcing imminent catastrophe. Often there is only a quiet groan moving through steel beams or a sudden fracture in concrete that signals the structure has begun moving beyond the limits of control. By the time those sounds reach the workers below, gravity may already be preparing to finish what the machines have begun. Before a building disappears, men must stand beneath it. Demolition is often imagined as a spectacle of collapsing walls and clouds of dust, but long before that moment arrives, crews move carefully through the silent interiors of structures that are about to cease existing. Every floor, beam, and column must be studied, measured, and prepared for the forces that will soon be applied. The workers who enter these spaces understand that they are stepping inside something already condemned. Demolition engineers arrive first. They walk slowly through corridors and stairwells, carrying structural plans and measurement tools, examining the hidden skeleton of the building. Concrete columns are inspected for cracks. Steel beams are studied where they meet the ceiling joints. Floors are measured to calculate how weight travels downward into the foundation. Each observation becomes part of the collapse plan. After them come the rigging crews. These workers bring the heavy hydraulic cylinders that will eventually push against the building's most important supports. The machines arrive in pieces: steel pistons, pressure hoses, pump units, and reinforced mounting plates designed to hold the cylinders in place. Inside basements and foundation levels, the crews position the equipment with careful precision. Each hydraulic jack must align exactly with the load-bearing points identified by the engineers. A piston placed even a few inches off its intended position can shift the entire collapse pattern of the structure above. When the cylinders are anchored into place, the pump operators take control. From outside the building, diesel-powered pumps begin forcing hydraulic fluid through thick steel-reinforced hoses. Pressure builds gradually inside the system. Gauges mounted along the control panels climb slowly upward as the pistons begin extending inside the dark spaces beneath the structure. During this phase, the workers inside the building remain alert. They listen. Buildings often speak before they fall. Concrete may fracture with a sharp crack as the first stress lines form inside the columns. Steel beams sometimes groan under shifting weight as the load distribution begins to change. Dust drifts slowly from ceiling joints where the structure is beginning to move in ways it was never designed to move. These sounds carry meaning for experienced crews. A single crack might be harmless. Several in quick succession can signal that the building is approaching the moment when gravity will take over from the machines. Workers positioned around the demolition perimeter watch the structure carefully. Radios crackle with updates from engineers monitoring the pressure levels in the hydraulic system. If the collapse begins earlier than expected, the order to evacuate the zone must move through the crew instantly. Because once a building begins to fall, there is no reversing the process. The men standing beneath it must already be gone. Yet even with careful planning, demolition crews operate in an environment where uncertainty is constant. Old structures often conceal weaknesses that appear only under pressure. A column may crumble faster than expected. A beam may snap before the sequence of hydraulic pushes has finished. In those moments, the workers closest to the machines are also the closest to the falling weight of the city itself. Every demolition plan begins with certainty. Engineers calculate load paths through floors, beams, and columns. Hydraulic pistons are positioned beneath carefully chosen points where the structure carries its greatest weight. The sequence of pressure increases is mapped in detail: first one support weakens, then another, until gravity completes the collapse exactly as designed. On paper, the process is orderly. In reality, buildings rarely behave exactly as their plans predict. Many structures scheduled for demolition have lived complicated lives. Walls have been removed during renovations. Reinforcing beams have been added to support heavy machinery. Concrete has been poured into areas never recorded in official drawings. These hidden alterations can transform a predictable collapse into a dangerous uncertainty. The moment hydraulic pressure begins shifting the building's weight, those hidden elements reveal themselves. A column expected to bend may remain rigid. A beam assumed to carry little load may suddenly take the entire mass of several floors. Stress travels through the structure along unexpected paths, searching for the weakest point where gravity can finally take control. Sometimes that weakest point appears far from where engineers intended. Workers stationed around the demolition zone learn to watch the building itself for signs of trouble. Cracks forming in unexpected locations. Dust drifting from windows on the wrong side of the structure. Steel beams bending outward instead of inward. Each signal suggests the collapse is beginning to move beyond the plan. One such incident occurred during the demolition of a multi-story industrial warehouse in the late 20th century. Hydraulic jacks had been placed beneath several primary columns along the center of the building. Engineers expected the upper floors to fold inward toward the middle, allowing the structure to collapse neatly within its own footprint. But the building carried a hidden reinforcement. Years earlier, a steel frame had been installed to support heavy manufacturing equipment. The modification was never recorded in the original construction documents. When the hydraulic cylinders began weakening the central supports, that hidden frame shifted the load unevenly across the structure. The building began to tilt. At first the movement was subtle. Windows cracked along the upper floors. Dust fell in thin streams from ceiling joints inside the lower levels. Workers watching from the perimeter noticed the western wall bending outward, exactly the direction the collapse had been designed to avoid. Within seconds the imbalance accelerated. Several floors dropped along one side of the building, dragging tons of concrete and steel downward toward the street. The collapse no longer resembled the slow inward fall engineers had planned. It became a violent sideways failure. Workers shouted warnings and ran from the edge of the demolition zone as debris burst outward across the pavement. The building struck the ground with a deep thunder that echoed through the surrounding blocks. When the dust finally settled, part of the structure lay outside the intended collapse boundary. Fortunately, nearby buildings remained standing, but the accident revealed a difficult truth about controlled demolition. Even the most carefully calculated plan can be undone by the hidden complexity of the structures it attempts to destroy. Gravity, once released, does not negotiate with engineering diagrams. In some demolition projects, a single structure is not the target. Entire sections of a city must disappear. Such projects often emerge from moments of urban transformation, when aging industrial districts give way to highways, when outdated commercial blocks are cleared for towers of steel and glass, or when municipal planners decide that an entire neighborhood has reached the end of its structural life. In these moments, demolition ceases to be the removal of one building. It becomes the erasure of an entire landscape. One such operation unfolded during the redevelopment of a mid-20th century industrial district that had once been the beating heart of a manufacturing city. For decades the block had been filled with brick factories, narrow warehouses, and aging office structures built close together along crowded streets. By the time the demolition crews arrived, many of the buildings had already been abandoned. Broken windows stared out across empty sidewalks. Rusted loading docks sagged beneath roofs that had not been repaired in years. Inside, machinery once used to stamp metal and assemble equipment stood silent beneath layers of dust. The redevelopment plan required something drastic. The entire block, 6 large industrial buildings and several smaller structures, would be removed in a single coordinated demolition sequence. Hydraulic systems would weaken the foundations across multiple structures simultaneously. Once the load-bearing points failed, gravity would pull the entire complex inward, allowing the rubble to settle within the boundaries of the site. Weeks of preparation preceded the final operation. Engineers surveyed every building, mapping the network of columns and beams supporting the structures. Hydraulic cylinders were positioned beneath critical supports inside basements and foundation levels. Control lines ran from each cylinder to a centralized pump system capable of managing pressure across the entire block. On the morning of the demolition, the streets surrounding the district were closed. Police barriers held back onlookers gathering along the outer perimeter. Emergency crews waited beyond the safety zone in case something went wrong. Above the rooftops, the sky hung grey and still, as though the city itself were pausing to watch what would happen next. At the command station, engineers began the sequence. Hydraulic pumps roared to life, sending pressurized oil through a network of reinforced hoses leading into the foundations below. Gauges climbed steadily as the cylinders began extending beneath columns that had supported the buildings for half a century. Inside the structures, pressure mounted slowly. Concrete cracked. Steel beams bent under shifting loads. Then the first building began to move. The western warehouse collapsed inward with a deep grinding sound as its central supports gave way. Seconds later, the neighboring factory followed, its floors dropping one upon another in a cascade of falling concrete. The collapse spread across the block like a chain reaction. 6 buildings fell in succession, each one surrendering to gravity as the hydraulic systems beneath them shifted their foundations. Massive walls folded inward. Roofs dropped through the hollow interiors. Clouds of dust erupted skyward as thousands of tons of material struck the ground. Within less than 30 seconds, the entire industrial block had vanished. Where factories once stood, there was only a wide field of shattered brick, twisted steel, and drifting grey dust slowly settling across the ruins. The silent giants beneath the foundations had completed their work. When the dust settles after demolition, the transformation of a city begins almost immediately. What was once a crowded block of factories or aging apartment buildings becomes open ground, an empty space surrounded by streets that once framed permanent structures. Within days, survey crews arrive to measure the cleared land. Soon after, construction equipment begins preparing foundations for whatever will rise next. Yet beneath this cycle of destruction and construction lies an industry rarely noticed by the public. Industrial demolition has become one of the quiet engines of modern urban change. Throughout the 20th and 21st centuries, cities around the world have repeatedly reshaped themselves through controlled removal. Old districts give way to highways. Warehouses become office towers. Entire neighborhoods are replaced by transit systems, commercial complexes, or residential developments designed for new generations. None of these transformations begins with construction. They begin with removal. The machines responsible for that removal rarely attract the attention given to the buildings that replace them. Hydraulic demolition systems operate in basements and foundation pits where the public rarely sees them. Their work happens quickly, often in the early morning hours before traffic returns to the surrounding streets. But the scale of their influence is immense. Entire skylines have been made possible by clearing the structures that once stood beneath them. Towers of steel and glass now occupying financial districts across the world stand on land that had to be emptied before their foundations could be laid. The silent giants of hydraulic demolition have performed that task thousands of times. The process has also grown more sophisticated with time. Modern engineers use computer modeling to predict precisely how structures will behave under hydraulic pressure. Sensors monitor stress levels inside steel beams as demolition sequences unfold. Remote control systems allow operators to adjust pressure levels from safe distances while buildings begin their final descent. Despite these technological advances, the principle remains the same. A structure built through careful engineering can be undone through equally careful engineering. Gravity remains the final force. The machines merely decide where and when that force will take control. Across modern cities, redevelopment continues to accelerate. Land grows more valuable as populations rise and infrastructure demands expand. Buildings that once represented the height of architectural achievement eventually become outdated, inefficient, or unsafe. When that moment arrives, demolition engineers step forward once again. Their machines wait beneath the foundations, quiet and powerful, prepared to erase what once defined the landscape so that something new can take its place. Cities often give the illusion of permanence. Stone towers rise above streets that appear unchanged for generations. Steel bridges stretch across rivers as though they have always belonged to the landscape. Office blocks, factories, and apartment buildings seem fixed in place, part of a skyline that defines the identity of the city itself. Yet beneath this appearance lies a quieter truth. Urban landscapes are temporary. Every structure, no matter how massive or carefully engineered, exists within a cycle that eventually leads to removal. Materials weaken. Designs grow obsolete. Land becomes too valuable to remain occupied by buildings that no longer serve the demands of the present. When that moment arrives, the silent giants return. Hydraulic demolition systems, hidden inside basements and foundations, apply the same patient pressure that has reshaped cities for more than a century. Their steel cylinders extend slowly against the bones of structures once thought permanent. Columns bend. Foundations fracture. Gravity begins its quiet work. The buildings fall. In their place, new foundations appear. Steel frames rise toward the sky once again. Few people who walk through modern city streets ever consider the machinery that made those transformations possible. Skyscrapers capture attention. Architectural landmarks become symbols of national pride. But the removal of the structures that once occupied the same ground is rarely remembered. Yet without demolition, progress would stall. The silent giants ensure that cities remain capable of changing. They erase the past carefully, making room for the next stage of urban life. Their work happens quietly, often beneath the surface, long before new construction begins. In that sense, they are not merely machines of destruction. They are instruments of renewal. And somewhere beneath the foundations of every modern city, the pressure systems that once erased entire blocks still wait, silent, patient, and powerful, ready for the moment when the skyline must change again.